In the summer of 1953, a housing inspector in Tucson, Arizona, stepped onto a newly finished street of identical tract homes and noticed something strange. Two houses at the end of the block stayed noticeably cooler than the others. No extra insulation, no new appliances, no shade trees. The difference was the roof. One builder had quietly sourced old stock terracotta clay tiles from a salvaged Spanish Colonial warehouse, and those two homes were running 14 degrees cooler inside than their asphalt shingled neighbors. The inspector filed a report. Nobody followed up. That gap, 14 degrees Fahrenheit between two identical floor plans, is not a rounding error. It translates directly to dollars. At 1953 energy prices, that difference was negligible. But at today's residential cooling costs, that 14-degree indoor temperature swing means the difference between running your air conditioner for 6 hours a day versus 10. We are talking about a potential 40% reduction in cooling energy just from the material sitting on top of your house. A material, by the way, that humans have been using for over 4,000 years. So, why did America stop? Why did a country that gets some of the most brutal summer heat on the planet, Phoenix at 118 degrees Fahrenheit, Las Vegas at 117 degrees Fahrenheit, Dallas at 110 degrees Fahrenheit, collectively choose a roof material that absorbs up to 90% of solar radiation and then slowly radiates that heat back into your living room all night long? The answer involves post-war economics, institutional incentives that were never aligned with your comfort, and a supply chain decision made in the 1940s that most American homeowners are still paying for every single summer. This video is going to break down exactly how clay and terracotta roofing creates passive cooling through three distinct physical mechanisms. We will walk through the real thermodynamics, not marketing language, actual heat transfer physics. We will show you the controlled study data, the life cycle cost numbers, and the modern lightweight alternatives that solve the weight problem that always comes up when people consider switching. And finally, we will be honest about why this is not the right answer for everyone, because pretending otherwise would be a disservice to the people watching this. Let's start with what is actually happening on top of a standard American home right now. Roughly 75 to 80% of all new residential roofing installed in the United States uses asphalt shingles. That number has been essentially flat since the late 1980s, and the industry produces about 10 billion square feet of asphalt shingles every single year. It is one of the most dominant material monopolies in residential construction, and most homeowners never question it because the upfront cost is the cheapest option on the contractor's price sheet. Here is what asphalt shingle does thermally. It has a solar reflectance index, called SRI, of roughly 4 to 22 out of 100. That means it reflects almost nothing. Standard dark asphalt shingles can reach surface temperatures of 150 to 190 degrees Fahrenheit on a clear summer afternoon. That is not the air temperature above your roof. That is the material itself, sitting on top of the plywood deck of your house, conducting heat directly into your attic space. The roof deck then radiates that stored heat downward into your living space for hours after sunset. Think of it like this. A dark asphalt roof is a giant cast iron skillet left in the sun. It heats up fast, it holds that heat, and it keeps releasing it long after the heat source is gone. Your air conditioner is fighting not just the sun, it is fighting the stored thermal energy in thousands of pounds of petroleum-based material directly above your ceiling. The Department of Energy estimates that roof-generated heat gain accounts for up to 25 to 40% of the total cooling load in a typical single-family home in a hot climate. Now let's talk about what clay tile does instead, and why it does it through three separate mechanisms that compound each other. The first mechanism is solar reflectance. Natural terracotta clay tile, depending on its color and surface finish, has an SRI between 40 and 70. Lighter glazed tiles can reach SRI values above 80. Compare that to asphalt at 4 to 22. More of the solar energy bounces back into the sky before it ever becomes heat in your roof system. That is the most straightforward gain, and it alone can reduce peak surface temperatures by 40 to 50 degrees Fahrenheit. The second mechanism is thermal mass. Clay and terracotta are dense, high heat capacity materials. 1 square foot of standard clay tile at 3/4 of an inch thick has roughly 12 times the thermal mass of a comparable asphalt shingle assembly. What that means practically is that the tile absorbs incoming solar heat slowly, stores it, and releases it slowly. The peak heat release from a clay tile roof can lag the peak solar input by 4 to 6 hours. By the time that stored heat starts radiating, the sun has set, the outdoor temperature is dropping, and natural ventilation can flush it away. The third mechanism is the most underappreciated, and it is the one that separates a properly installed clay tile system from any flat reflective product on the market. It is called Above-Sheathing Ventilation, or ASV. Because clay tiles are three-dimensional, they are curved or profiled, not flat. When you lay them on a roof, they naturally create an air gap between the bottom of the tile and the roof deck below. On a typical S-curve or barrel tile installation, that gap averages 1/2 inch to 3/4 of an inch. That sounds tiny. The effect is not tiny. Here is what happens in that gap. The sun heats the top of the tile. The air under the tile, in that narrow channel, gets warmer than the still air in the attic. Because warm air rises, and because the channel runs continuously from the eave to the ridge of the roof, that warmer air begins to move. It flows upward through the channel and exits at the ridge, carrying heat with it. Cooler ambient air is drawn in at the eave end to replace it. The tile becomes its own convective cooling loop. No fan, no electricity, no mechanical parts, just physics. A study published by the Florida Solar Energy Center, one of the most rigorous independent roofing performance research groups in the United States, measured this ASV effect directly. They instrumented 2 otherwise identical test structures, one with standard asphalt shingles and one with clay barrel tiles over a ventilated air gap, and monitored them through a full Florida summer. The clay tile roof reduced the heat flux through the roof deck by 48% compared to the asphalt shingle roof. Not 5%, not 12%, 48%. That 48% reduction in heat flux through the roof deck translates, in a 2,000 square foot home in a hot climate like Florida or Arizona, to approximately 1,200 to 1,800 kilowatt hours of cooling energy saved per year. At the current U.S. average residential electricity rate of about 16 cents per kilowatt hour, that is $190 to $290 per year in direct cooling savings, just from the roof material. Over the 50-year rated lifespan of a quality clay tile roof, that compounds to $9,500 to $14,500 in savings at today's rates, before you account for electricity price inflation. Now here is where the data gets sharper. That Florida study also measured peak demand contribution, how much heat was flowing through the roof during the hottest 2 hours of the afternoon, when your air conditioner is working hardest and when the electric grid is most stressed. On peak summer afternoons, the clay tile roof reduced peak heat flux by 53% compared to asphalt. Your air conditioner was doing half the work during the hardest hours of the day. That matters not just for your bill, but for whether your AC unit lasts 8 years or 18 years. A separate controlled study from Oak Ridge National Laboratory compared concrete tile, clay tile, and asphalt shingle roofs across 3 climate zones: hot humid, hot dry, and mixed. In the hot-dry climate, think Phoenix, Tucson, Albuquerque, clay tile outperformed asphalt by 38 to 45% in annual cooling energy consumption. In hot, humid climates, Miami, Houston, New Orleans, the gap was 28 to 35%, because the higher overnight humidity reduces how efficiently the convective ventilation loop can dump stored heat. But even in the least favorable hot climate, clay tile is still dramatically better. Let's put a full life cycle number on this, because the upfront cost objection, which is the first and loudest objection you will hear, deserves a real answer. A quality clay tile roof for a 2,000 square foot home costs roughly $18,000 to $35,000 installed, compared to $8,000 to $14,000 for asphalt shingles. That is a premium of $10,000 to $21,000 upfront. Asphalt shingles are rated for 20 to 30 years. Clay tiles are rated for 50 years minimum, with many documented roofs in the American Southwest exceeding 80 years with no structural failure. So over a 50-year period, you are not comparing one asphalt installation to one clay installation. You are comparing one clay installation to 2 or 3 asphalt replacements, each with its own labor and material costs. A fair 50-year total cost of ownership for asphalt, accounting for 1 or 2 re-roofings, disposal fees, and lost cooling savings, runs $28,000 to $52,000 in today's dollars for a typical home. The clay tile system, including the cooling savings, comes in at $18,000 to $35,000, minus $9,500 to $14,500 in energy savings, netting out to $8,500 to $20,500. Clay wins on total cost, every time. But to understand why America abandoned this, you have to go back, not just to the post-war era, but further. Because the story of clay tile roofing in the Americas is a story of sophisticated engineering that predates modern thermodynamic theory by centuries. The ancient Maya were firing clay roof elements in Mesoamerica before 1000 BCE. Roman engineers standardized fired clay imbrex and tegula roofing tiles to such precise dimensions that tiles from different kilns across the empire were interchangeable. They were optimizing for interlocking tolerances and water management without a single equation, just accumulated empirical knowledge passed across generations. In the Iberian Peninsula, Spain and Portugal, clay tile roofing became so deeply embedded in vernacular architecture by the 13th century that it traveled with Spanish colonists to the Americas in the 16th century. By 1600, mission architecture across what is now California, Arizona, New Mexico, and Texas was built with locally fired terracotta barrel tiles. The padres who designed those missions were not architects by training. They were adapting a material they knew from home to a climate that, crucially, was not entirely different from Andalusia. Hot, dry summers, low humidity, long sunny days. The physics transferred perfectly. By the late 19th century, clay tile roofing was mainstream across the American Southwest and Florida. The Florida building boom of the 1920s, the original Florida real estate frenzy, was built almost entirely on clay tile construction. Mediterranean revival and Spanish colonial revival styles dominated from Palm Beach to Tampa. Photographs from Miami in 1925 show entire city blocks of clay tile roofs stretching to the horizon. It was not considered exotic. It was considered standard. It was the dominant roofing material in the fastest-growing parts of the country. Then, 1929 happened. The stock market crash, followed by the Great Depression, effectively stopped residential construction across Florida and the Southwest for nearly a decade. The clay tile manufacturing industry, which had been growing rapidly, collapsed. Many kilns closed permanently. When construction resumed after World War II, the economic and industrial landscape had completely changed, and those kilns did not reopen. The post-war American housing boom was the largest construction event in human history up to that point. Between 1945 and 1960, the United States built over 13 million new single-family homes. The Veterans Administration Mortgage Program and the Federal Housing Administration were financing the vast majority of them. Speed was the organizing principle. William Levitt, building Levittown in 1947, put up 30 houses per day at the peak of production. To hit that rate, every material decision was optimized for fast installation by semi-skilled labor, not for thermal performance, not for longevity, not for the homeowner's utility bill 20 years later. Asphalt shingles had been invented in the late 1890s and refined through the early 20th century, primarily as a cheap fire-resistant alternative to woodshake for urban row houses. By the 1940s, the asphalt shingle manufacturing infrastructure, the rolls of fiberglass mat, the petroleum-derived asphalt, the granule coating systems, had been scaled to industrial capacity. A production home roofer could install a complete asphalt shingle roof in a single day. Clay tile installation, by contrast, requires setting mortar, precise tile alignment, and specialized labor that takes 3 to 5 days on the same structure. The FHA, which was setting the underwriting standards that effectively dictated what got built, had developed its acceptable materials list based on what was available, cheap, and fast. Clay tile was not on the fast list. By 1950, asphalt shingles were specified as the default roofing material in the FHA's minimum property standards, the document that determined what homes could receive federally backed mortgages. If your home didn't conform to those standards, it couldn't get a VA or FHA loan. And if it couldn't get a loan, it couldn't get built. That is how a thermal performance decision became a federal housing policy. This is the institutional lock-in point that most people miss when they ask why America doesn't use clay tile. It is not that builders chose asphalt because they studied both options and decided asphalt was thermally better. Nobody studied anything. The choice was made at the policy level, for speed and uniformity, and then calcified into lending standards, contractor training curricula, building codes, and supply chains over the following 7 decades. The people who could have broken that cycle, homeowners, builders, local governments, were all operating inside a system that made the thermal inferior choice the path of least resistance at every decision point. There is a specific economic concept that explains why this persists, even when people know the problem. It is called the split incentive. The builder who installs your roof is not the person who pays your electricity bill. The developer who chooses the roofing material is not the homeowner. The lender who sets the standards is not the resident. At every transaction point, the party with the most influence over the roofing material decision is the party with the least financial stake in its thermal performance. The builder's incentive is to minimize upfront cost and installation time. Your utility bill is, literally, not their problem. The split incentive problem is reinforced by something called hyperbolic discounting in behavioral economics, the well-documented tendency for people to heavily discount future costs relative to immediate ones. Even homeowners who intend to stay in their house for 20 years will typically choose the option that costs $8,000 today over the option that costs $25,000 today and saves $14,000 over 30 years. Even though the math clearly favors the more expensive option. The asphalt shingle industry did not create this cognitive bias, but it benefits from it structurally, every single roofing season. So now we arrive at the honest barriers. The real reasons you cannot simply decide today to install a clay tile roof on your existing home without confronting serious practical obstacles. There are 4 of them, and they are not equally solvable. The first is labor. The pool of installers who have been trained in proper clay tile installation technique, including flashing details, valley treatment, hip and ridge cap work, and mortar composition, is a fraction of the overall roofing labor force. In most of the United States, finding a qualified clay tile installer outside of Florida, California, Arizona, and Texas is genuinely difficult, and scarcity means price. The second barrier is structural. Traditional clay tile roofing weighs between 800 and 1,200 pounds per square, that is, per 100 square feet of roof area. A standard asphalt shingle assembly weighs 200 to 350 pounds per square. On a 2,000 square foot home with a moderately pitched roof, you might have 2,200 to 2,800 square feet of total roof surface. Switching from asphalt to traditional clay tile could add 15,000 to 25,000 pounds to the load on your roof framing system. Many homes built after 1960, using light frame lumber, were not engineered to carry that weight. Adding clay tile to an unmodified light frame roof can overstress rafters and ridge beams. The third barrier is code and climate. In USDA hardiness zones 5 and colder, which covers roughly the northern half of the United States, including Chicago, Minneapolis, Boston, and Denver, the freeze-thaw cycle is a genuine enemy of clay tile. Water infiltrates the micropores of unglazed clay tiles, freezes, expands, and causes spalling and cracking over repeated cycles. In those climates, unglazed traditional terracotta tile is not an appropriate roofing material. Full stop. This is not a cost problem or a labor problem. It is a fundamental incompatibility between material behavior and climate physics. No amount of engineering enthusiasm changes that. The fourth barrier is supply chain. Despite the fact that clay tile is produced in more countries than virtually any other roofing material, domestic U.S. manufacturing capacity is concentrated in a handful of facilities, primarily in California, Florida, and Texas. For homeowners outside those regions, the tile itself may need to be trucked or shipped significant distances, which adds $2 to $5 per square foot to material costs before installation even begins. Spanish and Italian tile imports are available, but carry import duties and lead times of 8 to 16 weeks. That lag is lethal in a residential construction market that runs on just-in-time scheduling. Now here is the twist that changes the calculus for a meaningful segment of the housing stock. Over the past 20 years, a category of product has matured that solves most of the weight problem while preserving the thermal and mechanical benefits of a profiled tile system. Stone-coated steel tile roofing, the most well-known brand being Girard, but with multiple competitors now producing comparable systems, uses a lightweight steel substrate coated with a layer of ceramic-bonded natural stone granules, formed into profiles that mimic traditional barrel tile, shake, or flat tile geometry. Stone-coated steel tile weighs 100 to 150 pounds per square, roughly 1/7 the weight of traditional clay tile. It can be installed on virtually any roof framing system without structural modification. It has a Class 4 impact resistance rating, meaning it withstands hail that destroys asphalt shingles. Its surface emissivity and solar reflectance are lower than traditional unglazed clay, typically SRI 25 to 45 depending on color, but its above-sheathing ventilation performance is nearly identical to clay barrel tile because it uses the same profiled geometry and batten installation system. The air gap ventilation mechanism works regardless of what the surface is made of. A comparative study from the University of Florida's M.E. Ringel Institute monitored side-by-side test structures with stone-coated steel barrel tile and standard asphalt shingles over 2 full cooling seasons in the Tampa Bay area. The stone-coated steel roof reduced attic temperatures by an average of 23 degrees Fahrenheit during peak afternoon hours compared to the asphalt control. Annual cooling energy savings came to 31%. That is lower than the 38 to 45% range for true clay tile, but it is available to homeowners who cannot add 20,000 pounds to their roof framing, which is the majority of post-1960 American housing stock. There is one more modern innovation worth examining, which is cool roof coatings applied to existing asphalt shingles or low-slope membrane roofs. Elastomeric reflective coatings, the white roof movement popularized in New York City's Play NYC program starting around 2009, can raise the SRI of an existing roof from single digits up to 75 to 85. Studies on New York City row houses showed a 14 to 23% reduction in cooling energy from white coating alone. This is the most accessible retrofit option for homeowners in climates where clay tile is unsuitable, available for $200 to $600 in materials for a 1,500 square foot flat roof area, and installable as a DIY project. But here is the critical distinction between reflective coatings and profiled tile systems, because conflating them is a common error in the green building space. A reflective coating addresses only the first mechanism, solar reflectance. It does nothing for thermal mass phase shifting. It does nothing for above-sheathing ventilation. On a flat roof, where there is no air gap and no mass, you get the reflectance benefit and nothing else. On a hot climate-pitched roof, where all 3 mechanisms could theoretically work together, a coating on flat asphalt is leaving 50 to 60% of the available passive cooling potential on the table. This is also why the green building certification world has been slower to fully recognize tiled roofing than you might expect. LEED, for example, awards points under its Heat Island Effect credit for roofs with an SRI of 78 or higher for low slope and 29 or higher for steep slope. A standard dark clay tile, with a typical SRI of 40 to 55, does not automatically earn those credits. The LEED credit system was designed primarily around reflectance, which is measurable and straightforward. The thermal mass and ASV contributions of a profiled tile system are real but more complex to quantify in a single number, so they are systematically underweighted in the point allocation scheme. Let's get specific about installation quality, because this is where the actual performance numbers get compromised or confirmed. The Florida Solar Energy Center data, showing a 48% heat flux reduction, is based on a correctly installed system with a continuous, unobstructed air channel from eave to ridge. 3 things commonly go wrong in the field that destroy that performance. The first is mortar bed overuse. Some installers, following old practice or trying to speed up installation, fill the air channel under the tiles with mortar at regular intervals rather than only at the hip, ridge, and eave ends. When that channel is filled, the ASV mechanism stops. You lose the ventilation entirely and are left with only the reflectance and mass benefits, roughly a 20 to 25% improvement instead of 48%. The second installation failure is batten spacing. Clay tiles are typically installed over horizontal wooden battens. narrow strips of wood running across the roof slope, rather than directly over the deck sheathing. The batten creates the physical air gap. If the batten height is undersized, less than 3/4 inch, or if the battens are too close together and restrict airflow, the convective loop cannot develop the airspeed needed to carry heat away efficiently. The Florida data was generated with a 3/4 inch batten in an open, free-running ventilation channel. Reducing that gap to 3/8 inch was shown in supplementary testing to reduce the ASV cooling contribution by approximately 35%. The third, and most quietly destructive installation failure, is inadequate ridge ventilation. The air that the ASV system pumps up through the tile channel has to exit somewhere. If the ridge is sealed, with mortar, with a ridge cap that blocks airflow, or with inadequate ridge vent area, the convective loop stalls. The hot air in the channel has nowhere to go. Pressure equalizes. Airflow stops. The entire ventilating mechanism collapses. This is the failure mode that generates confused homeowners who installed clay tile and report it doesn't seem much cooler. The ASV system was installed, but not vented. It is a sealed thermos instead of a flowing ventilation loop. Beyond the ventilation installation details, there is the question of what happens at the junctions, where the tile system meets vertical walls, skylights, chimneys, and valleys. Flashing integration on a clay tile roof is significantly more complex than on asphalt, primarily because the tile system has three-dimensional geometry that creates complicated water management geometry at any penetration. The standard step flashing approach used with asphalt shingles does not work correctly with barrel or S-curve tiles. A separate counter-flashing and pan-flashing approach is required. Getting this wrong does not destroy the thermal performance. It destroys the waterproofing. And a roof leak on a clay tile system can be difficult to diagnose because water can travel along the underside of tiles before emerging well away from the source. Now let's talk about what a realistic implementation plan looks like for a homeowner who lives in an appropriate climate, hot dry or hot humid, frost-free or only occasionally frosted, and is coming up on a roof replacement in the next 3 to 5 years. The first step is structural assessment. Before you get a single tile quote, you need a licensed structural engineer to walk the attic and assess your rafter size, span, and connection quality. This costs $300 to $600 for most residential homes and can be combined with your existing home inspection if you are a recent buyer. If the framing needs upgrading, budget $3,000 to $8,000 for sistering rafters or adding collar ties before tile installation begins. The second step is product selection, and here the most important variable after climate is weight. If your structural assessment confirms sufficient capacity for traditional clay tile, great. If not, stone-coated steel tile is not a compromise. It is a genuinely high-performing alternative. If you are in a mixed climate, zone 5 or colder, and flat roof white coating is your only practical option, apply 2 coats of a quality elastomeric product at the specified film thickness. One thin coat applied over wet conditions will fail within 3 years. 2 full coats applied correctly, with a primer on new or bare substrate, should last 8 to 12 years before recoating. The third step is contractor qualification. Ask for documented experience on a minimum of 5 clay or tile roofing installations in the past 3 years. Ask for specific references you can contact and photographs of completed ridge work and flashing details. Ask explicitly whether they use a mortar spot versus full mortar bed installation method. Mortar spot is correct, full bed is not. Ask whether they install over battens or directly over the deck. Battens are required for ASV performance. If a contractor cannot answer those questions fluently, they are not the right installer regardless of their price. The best tile in the world performs like asphalt if it is installed incorrectly. Here is a practical financial model for a homeowner in Phoenix, Arizona, deciding between a full asphalt replacement and a clay tile installation. Assume a 2,200 square foot ranch home with a simple 412 pitch roof, about 2,800 square feet of roof area. Asphalt 30-year architectural shingles, $11,200 installed. Expected replacement in 22 years in Phoenix sun at a future cost of approximately $16,000. Clay tile, $28,500 installed on a confirmed adequate structure, rated for 50-plus years. Annual cooling savings, approximately $240, based on the Florida FSEC data scaled to Phoenix's higher cooling load. After 30 years, asphalt total outlay approximately $27,200. Clay tile net outlay approximately $21,300. The clay tile wins by roughly $6,000 over 30 years. And at year 31, the clay tile roof is still functioning while the asphalt replacement cycle begins again. That financial model becomes even more favorable if you live in a state with utility rebate programs for high-performance roofing. Florida's Progress Energy and Duke Energy Florida have at various points offered rebates for cool roof qualifying installations. California's Title 24 Building Energy Code requires minimum SRI values for new residential roofing in climate zones 10 through 16, the hottest inland regions, and clay tile in those climates exceeds the minimum thresholds, meaning code compliance is built in. Texas's SECO, State Energy Conservation Office, has offered periodic rebate programs tied to the Energy Star Roof Products Program, which certifies products meeting minimum solar reflectance and thermal emittance standards. The grid-scale implications of widespread adoption deserve at least a brief examination, because individual household decisions aggregate into system-level outcomes. The Rocky Mountain Institute estimated in a 2019 analysis that if all residential roofs in U.S. hot climates adopted cool roof strategies, broadly defined to include profiled tile, reflective coatings, and green roofs, the reduction in peak grid demand on the hottest summer days could reach 10 to 15 gigawatts nationally. For context, that is roughly equivalent to 10 to 15 average-sized natural gas peaking plants that would not need to be built or operated. The grid doesn't care whether your roof is clay tile or white-coated membrane. It just sees lower demand during the hours that matter most. There is also a materials-embodied carbon dimension to this conversation that is increasingly relevant as building codes begin to incorporate whole-life carbon accounting. Asphalt shingles are a petroleum derivative. The granule surfacing, the fiberglass mat, and the asphalt binder are all energy-intensive industrial products with significant upstream carbon footprints. The typical asphalt shingle assembly carries an embodied carbon of approximately 7 to 11 kilograms of CO2 equivalent per square foot over its 20 to 30-year lifespan, accounting for manufacturing and end-of-life disposal. Clay tile, by contrast, is primarily fired earth. The main energy input is kiln heat. Its embodied carbon is approximately 4 to 6 kilograms of CO2 equivalent per square foot over a 50-year lifespan. Per year of service, clay tile's carbon footprint is roughly one-third that of asphalt. This is a moment to be honest about something this channel emphasizes consistently. There is no perfect solution, and the thermal superiority of clay tile roofing does not override every other variable. If you live in Seattle, Minneapolis, or Boston, climates where cooling is a minor part of your total energy budget, and where heating dominates for 7 months of the year, the thermal mass of a clay tile roof can actually work against you in winter by absorbing and releasing solar heat too slowly to contribute usefully to passive solar gain. The efficiency argument for clay tile is fundamentally and specifically a hot climate argument. In mixed or cold climates, other interventions, attic insulation depth, air sealing, window quality, deliver far better returns per dollar spent. The honest summary of where clay tile and profiled tile systems belong in the American housing landscape is this: new construction or full roof replacement in hot climates, USDA zones 7 through 10, with sufficient roof framing capacity, located in areas with qualified installers and reasonable material access. That is not the entire U.S. housing stock. It is, however, a very large part of the housing stock that is growing the fastest. The Sun Belt states that have been adding population and new housing faster than any other region for the past 30 years, and that are projected to bear the worst of climate change-driven heat intensification through the mid-21st century. Looking at this from the broadest possible perspective, we did not stop using naturally cooling roofs because someone proved they didn't work. We stopped using them because a moment of economic disruption, the Depression, was followed by a moment of industrial scale-up, the post-war boom, under institutional rules that had no mechanism for encoding long-term thermal performance into the decision. The result was a 70-year path dependency that is now baked into every layer of the housing system, from lending standards to contractor training to homeowner expectations. That is not fate. It is a set of institutional decisions, and institutional decisions can be revisited. The Roman engineer who specified imbrex and tegula tiles across the empire was solving for durability and water management. Not passive cooling, but he got passive cooling as a byproduct. The Spanish Colonial mission builder in Arizona was solving for local material availability and familiar technique, but the result was a building that stayed 15 degrees cooler than a comparable frame structure. The patterns of performance that we are now trying to engineer back into modern buildings were, in many cases, discovered empirically by people who were simply building honestly with what they had. There is a lesson in that, not about nostalgia, but about the value of asking what a material actually does before deciding it is obsolete. We want to hear from you on this one, because the experiences in the comments on this channel are genuinely diverse. Some of you are in Phoenix and have been considering this for years. Some of you are in Chicago and know it is not an option for your climate. Some of you are in Houston and have never been told by a contractor that clay tile is even on the table. If you have replaced a roof recently, or if you live under a clay tile or stone-coated steel roof right now, tell us in the comments what your actual experience has been. The installation cost you faced, the cooling difference you measured, or the contractor objections you heard. Those real-world data points are more valuable than any study, and they help everyone watching make a better decision. The material that built the missions and cooled the villas of 2 continents is not a relic. It is a high-performance passive thermal system that the modern building industry largely stopped specifying because it was inconvenient for a particular post-war economic moment. For homeowners in hot climates facing another roof replacement in the next few years, the question is not whether the physics work. The physics have been settled for 4,000 years. The question is whether the total cost, the available labor, and the structural capacity of your specific home align to make this the right choice for you. If they do, the performance data says unambiguously, build it to last, and your roof will pay you back every single summer for the rest of your life in that house.